Hey everybody, and welcome to Module 2, Topic 1. This is our Algebra Keystone Remediation course. We're going to be running through our enrichments. Today we're going to be talking about scatter plots and lines of best fit. So if you missed anything during your remediation lesson for this module or topic, or you just were absent that day, here are the exact notes that you would have gotten during that remediation class, so you can follow along and fill them out if you happen to miss it. So let's start off with some basics. Scatter plot is a plot showing multiple sets of points. And remember, points are ordered pairs on the coordinate plane. We have an x comma a y, so a dependent and independent variable that correspond to one another. So most scatter plots deal with positive numbers, so we only need quadrant 1. So we're really dealing with just this quadrant 1 that's on the coordinate plane, because we typically have an x value that's positive and a y value that's positive. Yes, we can have other quadrants involved, but for the most part, you're going to deal with the first one. A correlation is a relation seen when the line is graphed. So let's go with a relation seen when the data is graphed. So we're either going to see a positive correlation, a negative correlation, or a no correlation. And that's actually how it goes here. So if I were to try, and I'm not going to graph a line, we'll do that in the next section with trend lines, but if I were to graph a line here, we know that going up and to the right from the origin is going to be a positive correlation. This one is going to be a negative correlation because we're going down and to the right. So if I were to graph a line, we'd have a negative slope that's associated with that. And then when points are sort of scattered and there's no sort of rhyme or reason to how they're plotted on the graph, we're going to go with no correlation. Okay, so no correlation in that case. And there was an extra L there, so I apologize. There we go. So the first two graphs are considered to have a strong correlation. And if you ever take any upper level statistics courses, we can actually determine how strong a correlation is by something called a correlation coefficient. We're not doing that here, but we can actually mathematically calculate and provide a number based on how strong or weak these scatter plots are. But for right now, we're just going to use our best judgment. A weak correlation. We're going to go ahead and just sketch these real quick. So a weak positive correlation. We still have so this positive trend to our points, if I were to end up drawing a trend line. But as you notice up here, these points are rather close together. Here we still have a positive correlation, but our points are more spread out. Weak negative correlation is the same way. We're just going down. So we still have a general trend of going downward, but these points may be spread out just a little bit further. We still see that there's a negative slope to these points, but they might be spread out. So we're going to plot the data and identify a correlation here. So we have hours of daylight along the bottom, and then along the side here, we're going to end up using temperatures. And scaling is one of the biggest problems that we have when we're trying to do scatter plots. So on your scale on the left-hand side, excuse me, we want to make sure that we can get all these high temperatures on there. So typically what I recommend students do is look at the high value versus the low value and figure out what your range is. So if we're looking between the two here, we have 30 is sort of our low number, 71 is going to be our high number. So we have almost like 40 degrees that we have to sort of span here. So why don't we go by fives? And what this is called, we're just breaking up the scale here, and we're sort of starting at a higher value. So we're going to do the same thing, and let's start at just our low value. We can still get a correlation out of this. When you go to do a trend line, typically not the best idea to do a broken scale here, or a modified scale, because we want to see a correlation that's actually going on. Or I'm sorry, write an equation for a line, which we're going to be doing in the next section. So 30, 40, 50, 60, and 70. So there we're going to be able to span all of our points, and then we're just going to start plotting, and we can estimate their locations. So for 12 hours of daylight, this is our x, because time is typically associated across the bottom or the vertical or the horizontal axis, and then our quantities are going to be on the left-hand side. In this case, we're going to be temperature. So let's go ahead and write these out. So this is temperature in degrees, and this is hours of daylight. We already have that down there. So let's start with the first one, 12 and 55. So we go to 12, and we're going to sort of roll the whole way up here, and we know we go by fives on the left-hand scale. So this is 12:55. 10:41, this one we're going to have to estimate. So we go, there's approximately 41. 9.5 is going to be in between, so we're going to go the whole way up to 40. We have 11.5 and 45. So that one we can actually plot on the line, but in between on the horizontal axis. And then 13 we have is 57. 57, again, we're going to estimate its location on the y-axis. 1471, that's, boom, that's going to be one of our possible outliers that's up there. And then 830, that's our minimum, 830. So looking at this graph, trying to match it up to sort of the correlation graphs that we have up here, we can definitely say that we have a strong positive correlation, a strong positive correlation. Okay. All right, let's keep moving on. The next thing is we want to be able to make predictions using trend lines, not just being able to draw scatter plots is going to be sufficient enough. We want to draw a trend line and make predictions off of it. When you draw a trend line and you make predictions based on the line within the graph that you see, it's called interpolation. And we don't need to discuss that any further. But a trend line, or a line of best fit, is the best representation of all the points that are on the graph. A line that roughly has half above, half below of all the points, that generally shows the correlation of these points. So if we picture all the points blurred together, so this is what this sort of area is representing here. We create this sort of thick area in between with all of our points contained. The trend line should be right down the middle of it. There's usually about the same number of points on either side. So in this case, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So roughly the same amount. And the key thing here is it does not have to go through the origin. There are some cases, some examples that it makes sense that it should go through the origin, such as, say that you were at a manufacturer's plant and you were trying to figure out, okay, time is on the bottom, and then the vertical axis is going to be the number of products that you create. Well, at time 0, have you created a product yet? No, we haven't developed anything. So that should be 0, 0. That should be the origin. But sometimes it's okay if we do not have our trend line going through the origin. We can use this trend line to estimate data at other locations on the graph, so estimate values. So let's draw a scatter plot and draw a trend line and then answer the questions that are provided. So we have a distance along the horizontal axis, time along the vertical axis. So here we really have it's somewhat backwards because I said time is typically associated with the bottom, but it's okay. As long as we get them straight when we graph them, that's going to be sufficient enough. So distance is going to be our x, time is going to be our y. Let's go ahead and start plotting. These scales are already done for us. So we have our 30 miles, 50 minutes. We have our 20 miles, 34 minutes. Again, we're just estimating. 40 miles, 62 minutes. 15 miles, 25 minutes. That was a little high. Let's go down here. And then we have 45 miles, 65 minutes. 45, 65 minutes. And then we have 30 miles, 52 minutes. Oh, I'm sorry, I did that backwards. 30 miles, let's forget about that point. 30 miles and then 52 minutes. That's a lot better. Okay. And then we're going to have our 50 miles, 82 minutes. There's our 50. 50 miles and 82 minutes. So these points are rather close together. And when you draw your trend line, always use a calculator if you can. Again, we're thinking of this example here. If we're traveling distance and there's time associated with it, at distance 0, should there be any time? No. So this is one of those cases where we want to consider that the origin should be where we go through. So we're going to draw that trend line where we sort of cut these points in half, and we draw that. And again, we're just in quadrant 1. Predict the time to travel 5 miles. So we find our distance across the bottom here, and we sort of estimate, here's going to be our 5. We track up to that point and figure out what it represents on the horizontal, the vertical axis. So this, I'm going to say 10 minutes. Okay, so we found 5 on the horizontal and found on the vertical. Predict the time to travel 65 miles. So we go to 65 miles, and we're going to go ahead, go up to the line. It's roughly right about there. Hey, look at that, about 100 minutes. Again, and let me draw little dashes here. I looked up from here until I hit that line, and then I looked over to sort of give me my estimate of 100. Same thing with down here. Don't really have room, so let's talk about the next one. If we take 160 minutes, so now we're on this axis, how many miles did we travel? 160. I'm going to map myself over to the side here. Boom, we intersect, and it looks like it's going to take us 100 miles. Okay, so again, think about, are we looking for an X? Are we looking for a Y? Which axis are we going to be looking at first, and map over until we hit that or intersect that line. All right, so I'm going to go ahead and stop the video. This is for the first 2 sections. In the next video, you're going to see writing an equation for a line of best fit, and I will walk you through an example problem. All right.